been working on a project recently, and this is the prototype down here. And this will get its own video shortly. But what I want to talk about today is the power supply for this, and how I chose the chip that will go into that power supply. This project is supposed to produce a TTL level output, among other things, but I'd like to keep it really small and portable, so I'd like to use one of these coin cell holders and accompanying coin cell for the power supply. And that should work out fairly well, because the project is going to draw current in the sub-milliamp range, and since these have about 200 milliamp hour capacity, if we assume that you're not going to run the thing 24 hours a day, which you won't, then the coin cell will basically last the shelf life of the battery, which is great. If you have to replace this every couple of months, if you use it frequently, then that's perfectly fine with me. The only issue with that is that these are lithium coin cells, and therefore they only output about 3.6 volts when they're full, and it will drop below that when they're going close to empty. So we have to put a little boost converter somewhere into the project. Since there are many thousands of chips to choose from that are available from different distributors and manufacturers, we have to draw up a couple of additional specs. Besides, we want it to boost from 3 volts to 5. And these are as follows. I want this to be reasonably small. The whole circuit should be about the size of this coin cell holder here, because the whole project is going to be fairly small, and there's not going to be all that much other circuitry on there besides the microcontroller. So the battery holder and the boost converter are going to dominate the size, the footprint. So they're also going to determine the size of the circuit board, and I want this to be reasonably small. But I also don't want extremely small BGA packages, because I can't really work with them well here in my shop. So I would like something that is reasonably small, like a SOC23 or similar. I also want this to be reasonably efficient, so minimum about 60%, but ideally much higher than that, because if we're wasting half the current that's coming out of our battery, that's just not great. I also want this to be high-ish frequency, so above a megahertz would be great, because that will contribute to making the whole circuit smaller, because we can have the filter capacitor smaller, and also the inductor will be a little smaller then. And lastly, I want it to be reasonably cheap, so under 15 cents in the quantities that I'll order, which is about 10 to 50 chips. And goes without saying, it has to be available in that quantity. I don't want to have to order 50,000. So I went to LCSC, which is a distributor that mostly sells Asian brands and Asian manufactured ICs. And there's a lot of chips that you don't normally know, and their documentation is fairly good sometimes. Sometimes it's only available in Chinese, which makes it a little harder to work with the chip. But I put all these parameters in the parametric search, and I looked around a little, and what I finally settled on is the same sort of chip that they also use in these little boost modules that you can buy on eBay, and the chip is down here. If we can focus on that, it's this one. So it's not exactly the same chip, but I think it's same manufacturer, and it's at least some sort of derivative of that. And this chip is called the MT3540. So if we look at the circuit down here, this is reasonably simple. We just have a filter cap, V-in, our inductor, a diode, two resistors, and capacitors. Capacitors, I'm going to use ceramic multi-layer ones. This diode here is going to be the SS14, which is a Schottky diode. It's a bit overkill for this application. This is good for up to an amp, but I didn't want to order a smaller diode, and I have quite a large stock of these, so we'll just use that. So for the test circuit that we're going to build, we're going to take this schematic, and then later here in the data sheet, there is a suggested layout, and we're going to follow this pretty close, with the exception that I want to do this on a single layer board. So I'm going to, instead of having a via here to a dedicated layer of V out and V in, I'm going to basically route this around like this here, and V out around like this, and we'll just see how much worse it gets by doing that, but it should be fine. They also suggest in the datasheet that we're supposed to make this a rather large ground plane, but I think this is more an issue if you're actually pumping 500 milliamps through the thing instead of a milliamp, so should be fine there. The resistors, this resistor divider is calculated by this formula here, and if I plug in 110k here, then I'll get 36k with V out being 5 volt and the reference being 1.23. So now we have all our component values for this. I'll put this in a CAD program and make a little circuit board. So this is the little circuit board I made just to test this chip, and as you can see, this is basically the layout that they put out in the datasheet, but inverted and with bridges going here and there instead of dropping to a separate layer. So I think it's high time we test this and see if it actually meets our specs and the specs in the datasheet, which is probably not going to meet because the layout is a little different, and this is not ideal for high frequency applications in a boost converter like this. The traces are quite small for that, and it's also just regularly routed instead of using polygons like you're supposed to do. But we'll just see how it does and if it works at all. So let's just look at some basic parameters here. We've got the input voltage set at about 3 volts. And we get about 5 volt output voltage. That will be perfectly fine. So let's hook this up to measure the input current here. So question current is about 0.2 milliamps, which is a lot higher than the datasheet says, but this is almost acceptable because the product is never, or the project's never going to be on and not doing anything. We'll always be drawing some current, at least half a milliamp if it's on. So we're never going to just waste away these 0.2 milliamps here without doing anything. But let's see how efficient this actually is. So I set up a basic current measurement with the input power coming in here, going through the multimeter, going into the input terminal, and then the output of the circuit going through a resistor down into this multimeter here. And resistor is set to limit this to about a milliamp, so slightly below that, because this is where our circuit is going to work. And if we look at these numbers here, we're getting 0.8 milliamps out, and we're drawing 1.7 milliamps into it at 3 volts, which is the lower limit of our supply voltage. And if we plug these numbers into the equation to calculate the efficiency, we're getting 0.8 by 5 over 1.6 by 3. We're getting 83% of efficiency, which is slightly below what the datasheet says the converter will typically deliver, but it's still very much alright, because we're working down in the very low current range here. This converter, where it's really good, and there's even a graph here in the datasheet, it gets really the best efficiency at load currents of about 100 milliamps or above that. And then also we're working against the lower limit of the input supply voltage. We're at 3 volts and the converter only goes down to 2.5. So we're right here somewhere. And we're actually getting slightly better performance than what we'd expect from the datasheet. So I'm pretty happy with that. And I think the only thing we have to look at now is what's the actual output regulation. Is there a lot of ripple on there? Can we accept the amount of ripple that's on there? And if that also works out all right, we can put this on we can put this into an Eagle design block and then just plop it into the final project. This is the circuit with the 0.8 milliamp load hooked up to the oscilloscope, and we're currently on 100 millivolts per division horizontally, vertically. And we can see this is fairly noisy. There's quite a bit of ripple on there. So in the final design, I'd either add a larger capacitor and see if that reduces the ripple somewhat, or I might even put in an RC filter stage, because this is a little over what I deem acceptable.